So, good evening, everyone. It's a pleasure to have you all here today. We are going to start our talk of this week from the Artificial Intelligence Group at the Institute of Computing at Unicamp, Brazil. We have the pleasure today to have the company of Dr. Jesus Pulido. He is going to talk to us about data science at scale. He is going to discuss some interesting problems that he deals with in the Los Alamos National Lab where he works, and also shows some very cool techniques to deal with data, especially when you have data at scale. Dr. Jesus Pulido did his PhD in California, right?
Yes.
He is now a research scientist at the Los Alamos National Lab as part of the Data Science at Scale team. As I said, he received his PhD in computer science at the University of California in Davis under Professor Bernd Hamann. Dr. Pulido specializes in data analysis, data reduction, visualization, high-performance computing, wavelets, and multi-resolution methods. He has an experience in applications with different image sensors, astronomy, turbulence, and cosmology. Dr. Jesus, thank you very much for accepting our invitation. Thank you, Audia, for suggesting Dr. Jesus. The topics that he is going to talk to us today are very, very dear to us in our lab and also in our research group. So, Dr. Jesus, thank you very much for accepting the invitation, and the stage is all yours. Feel free to start sharing your screen.
Hi. So thank you once again, Aurea and Anderson, for the invite. So I'm glad to give this talk. So that's a very nice introductory, I guess, a summary of my background. So today's talk is going to be, I titled it Data Science at Scale, Feature Analysis and Comparative Visualization. And here's a very quick outline of what I'm going to cover today. Basically, what data science is to us and what makes it at scale, how we perform feature analysis to perform meaningful data analysis, some of the tools and frameworks that we use that are open source and free to use, a few examples of comparative data reduction and comparative visualization with respect to data science, and a bit of a summary and sort of some open problems that I'm going to pose that are still sort of work in progress and feature areas of research that might be interesting to everyone. So Anderson already made a very nice summary about me. So I got my PhD at UC Davis under Professor Bernd Hamann, and I got my bachelor's at UC Merced. And I already have a summary of my research interests, but I also have a summary of some of my recent publications and soon to be published, for example, supercomputing and ISAB. And I figured I'd throw kind of a cool picture, a cool picture of myself and me snowboarding. And if you can see my camera, I don't think you can, but my current snowboard is right behind me, propped up to the wall. So a bit of an introduction of who I am and what I do, also to add. So I'm a staff scientist at the Los Alamos National Laboratory. I'm part of the Applied Computer Science Group, CCS7, and sort of as a sub-team, I'm part of the Data Science at Scale team. And you can find us at our website at dsscale.org. And please mind, it's maybe a year or two out of date, but the publication should be up to date. So I joined the Los Alamos National Lab early this year in February. So I'm a relatively new staff scientist. So I'm working on some cool new projects and getting some cool new results. So to summarize what our team focuses on, so we have a pretty diverse team of about 17 plus or minus one postdoc, 17 staff. So our main focus is on data visualization and data analysis. We do a lot of work on data reduction. That includes sampling methods, lossy and lossless compression, and also machine learning methods. Uh, we do topological analysis. We do research on scientific ray tracing. We work on programming models. So specific to parallel, high performance parallel visualization programming models, and we do a lot of tools and frameworks that helps us achieve all of this. And here's a nice visualization of one of the deep water impact data sets that we visualized about 3 years ago. And it was this is a pretty large data set that was pretty challenging to visualize. So what is data science? So I took this definition off of the internet just to give sort of the general definition of what's sort of the known. So what is data science? So data science is a field that uses scientific methods, processes, algorithms, and systems to attract knowledge and insights from many structural and unstructured data. And data science is a very general term, and different fields have different definitions of data science. So our definition of data science for the Data Science at Scale team so data science is sort of the act of creating meaningful frameworks and algorithms to provide analysis to domain researchers in data massive environments. So essentially, we're working with very massive scientific data, and we're trying to understand that data for what it is. So sort of reduce that data down to a cognitive, human understandable level. And the biggest challenge that we have here is we are dealing with this massive data reduction problem. So the question is, how do we perform meaningful data reduction? And just to give an example on the scale of data and what makes this even more difficult is, I want to give an example of some of the, for their time, some of the top or even top 5 supercomputers in the world, all hosted at Oak Ridge National Lab. So in 2013, this was Titan. 2018, this was Summit. And coming next year, maybe 2022, this is going to be Frontier. So within their respective eras, there were the top or the top 5 supercomputers in the world. And what I want to point out is this sort of scaling between peak compute performance and the peak storage. So at any time between generations, we would always have a 7.5 to 10 times improvement in peak compute performance. And this is sort of simulation computational data being processed insanely quickly. So generation over generation, we've seen this improvement for compute 7.5 to 10 times. But for storage, you can see the storage is sort of lacking behind. So instead of a 7 to 10 times performance, we're getting about 2.5 to 4x performance. And actually, within the spec sheets for Frontier, they outright say expect a 2 to 4x performance. And it's this disparity that makes it very difficult to decide what data are you going to write to disk and what data are you going to save for analysis when you want to do this solve this data science problem. So it's pretty clear that we're not able to save everything that we simulate in these massive simulations. We're not able to save to disk just because we don't have the capacity or the bandwidth to do so. So we have to be very selective about the type of data or the type of analysis that we do alongside the simulation. And that's sort of leads on to going back to the how do we perform meaningful data reduction question. So our current answer to this and what we've seen from the previous generation to the current generation, already seeing this disparity in compute versus I/O, is we've adopted the idea of in situ processing or running subroutines alongside the simulations. And how do we perform? So within these subroutines, one of them is, for example, performing data visualizations of the data without writing them to disk. So you do a visualization of a subsection of the simulation, and then you write out the image rather than writing out the data itself. And this is sort of a one-time deal. So it should be very critical to select the best visualization, because you only have essentially one chance to do this when you do a massive simulation. What does it mean to perform meaningful feature analysis and data extraction? And also another take on this is, how do we perform meaningful numerical data reduction? So there's been ideas and use cases for lossless and lossy data compression. So rather than trying to just generate an image and hope this image is good, how about we losslessly save the state of the simulation to disk with some acceptable amount of loss? And what does it mean to have an acceptable amount of loss, and what does that entail? So I'm going to cover these topics and the tools that we use to do this. So some examples of feature analysis. So this is one of the turbulence data sets and simulations that I work with here at Los Alamos. And this is a temporal visualization of the density of two fluid simulations interacting. So you have a very high density fluid and a low density fluid, and you sort of seed them, and then they interact with each other, and then they mix. They form this mixing behavior. And we're trying to essentially understand this behavior. So step one, we could just do outright visualizations of this. And this is one of the examples of just doing a generative visualization of the density behavior within this turbulence simulation. And then to perform meaningful feature analysis, for example, one of the ways the domain researchers are trying to understand the interaction between different fluids and the physics models are these definitions of features specific to sheets, tubes, and blobs. And we found through research that we can use various wavelet methods and the native multi-resolution capabilities of wavelets to extract these sheets, tubes, and blobs. And this is one example of a very important feature to extract and to run during a sim, where rather than just doing a general visualization and sort of not knowing what you're looking at, we could do this targeted feature analysis, extraction, and visualization while the simulation is running. And here I highlight several examples of sheets, tubes, and blobs. And sort of switching domains for cosmology. They simulate essentially the creation of the universe. So from the beginning, 13 billion years ago, up until today, they run this massive simulation, and they track essentially here the feature of interest are halos. So halos are these clusterings of matter that occur during the simulation. And it's these formations of these clusters that are the features of interest for these domain researchers. And what we've done since to help improve that is we've essentially, sort of through programming models, we've developed sort of high performance parallel algorithms to help speed up this halo identification process during the simulation. So while each time step is being ran, every other time step we're running we call the halo finder to extract and write out these specific features. And in the near future, we're also doing the writing out of these features to disk, but also this visualization on the fly as well, at more frequent steps, because doing visualization is a lot cheaper than doing data intensive IO to disk. So those are some examples of feature analysis. So I'm going to go into some tools and frameworks. You may be familiar with some of these if you're in the data visualization field. So one of the most popular tools that we use here at Los Alamos is ParaView. So ParaView is sort of a front-end interface that enables a user to perform a massive amount of different data visualization, both qualitative and quantitative techniques. So if you want to visualize your data right away, ParaView has over 100 data readers. So almost any simulation data type is supported by ParaView nowadays. And you can read it into ParaView, you can perform some nice volume visualizations. In this example, an isosurface contour visualization. And this allows for an interactive way of creating these visualization pipelines, so then that down the road you might want to set up a certain pipeline, and there's a lot of scripting behind this that I'm gonna cover next. So this is sort of the front end of the visualization toolbox that we use. So one of the back end toolboxes that we use alongside simulations is called ParaView Catalyst. So ParaView Catalyst is sort of the back end version of ParaView that enables you to use all of the wide visualization techniques that the front end allows, sort of in sort of a headless mode. So you're able to perform this visualization analysis when a simulation is running, and it's a simple implementation to sort of integrate into any existing simulation. Most of the larger simulations that we work with have already a ParaView Catalyst adapter, which essentially implements an initializer, an execute function that runs along the simulation stepper, and then a finalize that's sort of a cleanup step. And the way to set up these visualization pipelines, you use the front end to set up essentially a script. It could be either a C++ code or a Python script, which then the simulation will point to when it calls the Catalyst execute function. And it'll reproduce whatever visualization that you had within the interface. It'll reproduce it at regular time steps during the simulation. And this is very beneficial because, like I mentioned before, it's a lot cheaper to perform a single visualization than to dump out an entire data set to disk. And ParaView and Catalyst has very efficient parallel visualization algorithms to try and minimize the rendering time to perform these different functions. So essentially, Catalyst, its main usage is to produce images during simulations. So sort of the next evolution of that is called Cinema. So cinemascience.org. So Cinema is it's a bit of a fancier. So to be specific, so Cinema is a standard for generating image databases. So let's say you're doing a bit of an explorative visualization for a brand new simulation, and you may not know what you want to visualize. So what Cinema provides is a standard where you can control a camera and do several different visualizations at one time. So essentially, the simple case is at a certain time step, you set up a Cinema instance within Catalyst. So this is sort of an extension of Catalyst, and it'll essentially do a 360-degree camera fly through of the data and render those images and save them to disk. And then that's sort of the online component, the in situ framework component of Cinema. And because it's a standard of writing this out to disk, you could use sort of an offline reader, say ParaView or an HTML interface, to be able to play back and visualize these results. So it's a standard to visualize some of the images that you write out to disk. And I want to show a quick example of I mean, if you could go on cinemascience.org, there's several examples. This is one of the examples of the capabilities. So on the left side are all images generated in situ during one of the simulation runs. And this is just a very simple visualization. And this is sort of the interface, the web interface for Cinema. And what it's doing here, essentially, it's just loading images. So these are images already generated, written to disk during the sim. And the web interface simply just reads them and lets you explore and parse through the data. And this is sort of, like I mentioned, it's a bit of a brute force approach where you try to capture all of the possible angles and different possible values during your sim. And it just lets you browse it sort of carelessly without having to load the entire data set back onto your local computer. And you can run this off of a phone browser, a laptop. It's essentially just this is an image browser. So it's really low cost, very simple to use, and it's very helpful for domain researchers, since domain researchers, they don't have time to set up the full ParaView client and have to load in the data and get the pipeline working. So we provide this to domain researchers to do a very simple and easy exploration of their data. So that's Cinema. So I mentioned the idea of data reduction, of actual numerical data reduction, and we have a tool that we created to do this explorative data reduction. So this tool is called Foresight, Analysis That Matters. So this is a framework for comparing different numerical data reduction methods. And we say analysis that matters because what we've seen in the past is there's existing frameworks that do this, that compare different compression methods, and they compute standard metrics, like MSE, PSNR, relative error, absolute error, these sort of comparative numerical metrics, statistics. Other methods already do this. So where analysis that matters comes into play is we try to also perform and use some of the analysis techniques that are used by these simulations as well. So if we're looking at cosmology data, some of the features that they're interested in are the preservation of halos. So I mentioned halo as a feature previously. So they want to make sure that when you do, say, lossy numerical data reduction, that you don't affect the integrity of these halo structures, because these halo structures say a lot about the simulation, and sort of trying to verify sort of their numerical and improve their numerical models. So sort of in general, Foresight allows different data reduction algorithms, both CPU and GPU. We have, and this is all free open source to use. So we have currently within Foresight, we have CPU implementations of lossless BLOSK. If you're familiar with scientific compressors, we have SZ, ZFP, FPZip, Isabella, and we have GPU versions of SZ and ZFP. So you could do a bit of a CPU versus GPU analysis, and then also you could compare all the other CPU methods. And then not listed here, we also have data sampling methods. So if you have, say, a particle data set, you could do data sampling and you could compare that versus these traditional compressors. And then also we have machine learning based methods. So we have autoencoders, and they're not here, but we recently had this framework accepted as a full paper at Supercomputing 2020. And all I have to say is look forward to that talk in November. General admission is free, so anyone is able to join. Look forward to that talk. I'll have some more details at the very end. But in that paper, we compare essentially traditional compressors, lossless compressors, machine learning autoencoders, and sampling methods, and we show how that's all possible within the realms of this framework. One of the examples that we gave also is, what does it mean to have analysis that matters? So on the left side, you have this original data set of a cosmology simulation. The same data set compressed to some amount, let's just say relative error 25. It's kind of hard without giving context and going deep into this paper, but we've compressed this data set a little, and then we compress this data set a lot. And as you can see visually, visually these look identical. But what we found when we did further derivative analysis was that essentially none of these lossy compressed methods fall within the realms of acceptable error when you want to do further halo analysis. So this is one of the metrics that the cosmologists love to compare, and is power spectrum density. So this is basically a Fourier analysis on the data, and they want to see the effect of lossy compression on the different frequencies for the different scales within this Fourier analysis. And this is sort of a relative analysis. So a one-to-one ratio is a perfect reconstruction, and you see the original. And one of their criteria is you must be within 0.01 relative power spectrum error to not have to affect the derivative analysis that's being done with this data. And it turns out that although visually the data looks fine, numerically the data isn't accurate enough to perform subsequent analysis. And we try to push within the paper, we try to push towards more rigorous and meaningful metrics and analysis. So yeah, and this sort of goes further into that idea. And here's a very quick table of the different methods, the scalar fields and methods that we use to compare. And and important, the compression ratios. So this example, we use BLASK, FPZip, Isabella as ZFP. We sort of outline the best methods compression ratio wise, the absolute error. And the important stuff is down here, where we look at the different halos and we analyze the different halo regions. So we take the original data set, we compute the halos, and then we take the lossy version of the data set and try to compute the same halos. And then we do a original halo versus lossy halo analysis. And we try to fall within this 0.01 ratio. And you can see here which methods hit this criteria, which methods are within this boundary. Anything above is sort of it's sort of too lossy for any derivative analysis. And you can see here the effect it has on halo masses. And this is also another power spectrum ratio analysis. So 0.01, which is it's sort of outside of this range, but all of these methods are within the power spectrum analysis, but some of these fall outside of the range for the halo mass preservation analysis. And like I said, look forward to more results at SC 2020. I'll cover that later as well. And now I'd like to go into comparative visualization. So this is a bit of departure from the whole data reduction idea, but essentially here we're trying to use data analysis techniques to try to compare these two simulations. So I call it Exasky cosmology simulation. So this is part of the ECP Exasky project. So here we have two fundamentally different simulations, and they're both trying to achieve the same thing. They're trying to simulate sort of the cosmos, where things began, up until where we are now. So on the left side, we have HACC. This is the Hardware Hybrid Accelerated Cosmology Code, and this is a Lagrangian-based code. So it's a particle-based framework for computational cosmology. And on the right, you have a Eulerian-based code. So this is an adaptive mesh hydrodynamic simulation code. So the takeaway here is on the left, you have a particle-based code. That's what a Lagrangian point of view is. So at the particle level, they're simulating these particles individually. And on the right, you have this adaptive mesh refined grid-based code. And it has a Eulerian point of view, where instead of looking at particles, you're looking at the entire region. You're trying to simulate the entire region with a certain, say, physics concept. So the goal here for this comparison is you have two different simulation codes, and they're trying to cross-validate each other. They're both trying to reach the same end goal to simulate up until where we are today in time, but they have two different fundamental methods. And part of this project is we're trying to compare and cross-validate, and they're trying to validate each other. The one is more of the lead code, and the other one is more trying to validate against the other. So HACC is sort of the lead code currently, and Nix is trying to validate to HACC. So part of this workflow is we're essentially comparing a particle data set versus a grid data set. So how do we do this? First, we want to do general visualization for exploration. So we just want to visualize these data sets and see what they look like, and see if A matches B at the general level. Next, we want to do a feature-specific analysis, and in this case, we want to extract the top 10 to top 20 most massive halo, these cluster regions. We want to extract the top 10 most massive regions and visualize and compare their evolution over time. And then next, we want to also compute these, they call them phase diagram plots, but they're these density versus temperature phase diagram histograms. And they say certain things about the sort of the physics going on behind these simulations. And to do a one-to-one comparison, we need to reach a certain consensus on which format are we going to use. So either we compute the particles, these particle data sets onto a grid, sample them onto a grid to do a grid versus grid, or we do a grid data set and compute convert the grids onto particles and do particle versus particle. So this took a bit of back and forth with the domain researchers. In the end, we agreed on doing sampling the particles onto a grids because we found that to be more accurate. So because the particles have higher precision, just because they're essentially particles have infinite precision versus these grids, it's a lot more accurate to do a particle to grid sampling versus doing the inverse, grid to particle, just because grids are lossier in nature. Even though you do adaptive mesh refined grids, they're still not as fine precision as the particles themselves. So some of the tools that I'm going to go over and also show examples of are ParaView for comparing these different halo regions of phase diagrams, and also not going to show it here, but we also use cinema databases. Like I mentioned before, it's a lot easier for the domain scientists to sort of play with these simple sliders without having to have this complex and sort of scary interface with hundreds of different filters. Instead, they can just play around with this simple database that gives them all the points of views, and they could see the different comparisons being done. So part of the visualization workflow, so this is the workflow that we came up with. So we take this adaptive mesh refined grid and we sample it onto the finest regular grid possible. So for example, NICS, a simulation might start at 512 cubed, and as the simulation continues, it'll refine certain regions to finer and finer scales. So it'll refine it up to 1024 cubed, up to 2048 cubed, and then essentially some of the finest regions might be 2048 cubed. So what we do here is to simplify this analysis, we sample we resample the AMR grid onto the finest regular grid. So in this case, we create a 2048 cube grid. So then we take the HAC particles and then we sample them onto the same equivalent grid, the same box size of 2048 cubed. And there's several interpolation methods that we could use to do this. So the simplest method is NGP, which is the nearest grid particle. So whatever the nearest particle lands on, that's what that grid's value is going to be. There's another more complex method called smooth particle hydrodynamics, and this is a method internal to HAC that HAC. So some of the internal routines inside of the HAC simulation could use SPH interpolation. So we decided this is a more appropriate way when we do these visual comparisons as well. So third, we want to, like I said, we just want to get a global point of view of the visualization and see what it looks like. And this will be important coming up in the next slide as to why we can just do this. Step 4, we extract the 10 most massive halos and we extract the region around them to get a good sample area when we compute our statistics. Then we want to visualize these halo regions, and then we perform these phase diagram computations. This is sort of a general visualization just for exploration. So this is one of the reasons why in these constantly evolving simulation codes and improving simulation codes that you want to do general visualization. So up until we did this, sort of the domain researchers behind the NICS AMR code were simply just computing statistics. And they were finding some discrepancies in the way that the temperature was being refined during the simulation, but they couldn't quite figure out what was going on. So we came in and we did the simplest thing possible. We did a simple visualization. In this case, we did a slice visualization. This is the log scale mapping of the temperature on the right. And right away, we found something visually wrong. You can see these noise artifacts occurring. And we brought this forth with the NICS researchers and developers, and they instantly knew what was going on. So it turns out that the way that they were refining temperature wasn't using the correct method, and it was just a bug in their code. And we helped them fix this bug just by simply visualizing the data set and showing them this. And they instantly knew what it was. So this is one sort of thing that's sort of hidden behind statistics. So this error was within the statistical error within their models, but they had never seen what it actually looked like. And it wasn't until they saw what it looked like that they were able to figure out the problem, and they fixed it in subsequent versions of it. And on the left is sort of a fixed version. So here's a refined region, a halo region, and this is what it looks like. It's nice and smooth, and it behaves as it should. So now I'm going to show some examples of Halo region visualization. So like I said on the left, we're trying to compare Nix and Hack, and we're trying to do a bit of cross-validation. So on the left side, you have the main takeaway from this is we're trying to compare how different AMR levels within Nix affects sort of the evolution of halos. So on the Hack, like we said before, Hack is a particle-based code. So it essentially has infinite resolution. So when we sample to a grid, it looks the same. On the left is Nix. So I'll try to play them again. And this is sort of an orbit visualization of what it means to do one AMR level of refinement, 2 AMR levels, and 3 AMR levels. So as you can see, as you increase the number of AMR levels within the subgrid models, the accuracy of the halo regions improves. And this is still an ongoing piece of work. So we're going up to 4, 5, 6 different AMR levels. And what we're trying to see is at what point do these subgrid models fall apart? So that's what we're trying to validate here. And 3 levels clearly wasn't enough because they still look great at 3 levels. So we're trying to do a follow up with 4, 5, 6 different levels of AMR refinement. So to add to this, they compute these phase diagrams. So on the left side is Hack, and on the right is Nix. So what these phase diagrams are, they're essentially 2D histograms comparing the log of temperature versus the log of density. And they want to quantify the behavior of the particle-based code Hack versus the grid-based code Nix. And here you can see there's a lot of smoothing going on in Nix. And I think one of the outcomes of this was because there weren't enough AMR refined levels on Nix, there's a lot of over smoothing happening where there's a lot more coarseness in Hack because this is a particle-based code. And our workflow essentially computes this during the ingestion of the data. So it automatically computes these different phase diagrams, and it lets them know how to tweak and refine their different subgrid models for Nix and what that means with respect to Hack. And we could also compute these phase diagrams for the different halo regions. This is halo 0, for example, halo 0 being the most massive halo within the data set. And here we see the evolution of the phase diagram for the halo. So this is Redshift 5, 4, 3. A bit of a reference. So Redshift, I believe that the start of time when the Big Bang happened, this is 13 billion years ago. That's Redshift about 1080. So the simulation starts at Redshift 1000, and it goes and it sort of goes down up until Redshift 0. So Redshift 0 is today in terms of the simulation, and this is sort of reaching near towards what towards what today is. And this is important because I actually forgot to mention this. So the way that they try to validate these simulations is currently all we have is this observational science. So we have these ground space telescopes that look up into the sky and take many pictures. And we have these very massive sky surveys. So the purpose of these simulations is we're trying to simulate the universe up until today. So once we reach Redshift 0, there's ways to generate these synthetic sky surveys. So down the pipe, what they're doing is they're comparing synthetic sky surveys versus ground telescope observational sky surveys, and they're doing a bit of validation between each other. So that's sort of the big picture take of what's going on here. And this sort of, these phase diagrams boil down to some of the physics going on in the background. It's a bit over my head since I'm sort of the analysis person, more focused on the techniques for visualization and sort of like data science. But this is extremely helpful for the domain researchers to generate during these comparisons. And also what we provide to the researchers is sort of this sort of state of peer review where we're able to compare sort of Nix versus Hack different halo regions. And I mentioned before, one of the goals is to compare the evolution of the different halos. And if you recall the previous slide, these phase diagrams, the bottom, we're able to actually generate these phase diagrams, sans the coloring, but we're able to generate these phase diagrams. And I want to show an example of this current state here. So this is the same ParaView instance where we have this halo region. And on the bottom, we have phase diagram A and phase diagram B for both HAC and NICS. And here we could do actually interactive comparative analysis here and see how these different halo regions compare. And you could go back in time as well. I don't have them annotated, but we could essentially visualize the evolution of this halo from, I believe this is Redshift 20 to this is Redshift 20 up to Redshift 5, 4, and Redshift 3, which is the last time step of this simulation. That's when the simulation halted. But essentially, one of the cool things about this, and what's really helpful for the domain researchers, is its capability of selecting regions within the phase diagrams and mapping them to the visualization itself. So one of the things that came up during our sort of face-to-face meetings back when face-to-face meetings were more acceptable was we showed them this tool, and they were kind of interested in the behavior of this region here. So they want to essentially compare this HAC behavior here versus this NICS behavior here. So ParaView gives you this capability of being able to select these points that fall within this histogram, and it maps them to this visualization here. And yeah, so this was really impressive for them, because this sort of confirms some of the refinement subgroup models that they were trying to sort of cross-validate. And they right away knew what these regions corresponded to when they showed up within the 3D visualization. And unfortunately, it's a bit buggy, and this sort of framework is a bit of work in progress. So the lack of color is one of the things, but being able to show both regions at the same time is another. But you could also do the same for this region as well. So if you want to visualize the high density, high temperature regions, which should correspond to sort of the centers of the halos, you can sort of pick this out, and on this end, you could see sort of the center clustering of the halos. These are the high density, high temperature regions. And you could also do the same for this other, the right side for NICS, to see what these phase diagram mappings map to. So this is one sort of cool little interactive use case that's really helpful for them and for them to sort of play around with, and yeah. So that's ParaView, a bit of showcasing of what it's capable of. So to conclude everything, so data science and data science at scale, the way we see it, essentially, we see this as a large scale visualization and numerical data reduction problem. We're trying to take these massive data sets and we're trying to reduce them down to a human understandable level through various algorithms, tools, frameworks. This is what we essentially specialize in. We're constantly evolving and improving our tools and coming up with new algorithms. Some of them that I don't work on, but that the team is definitely working on and improving. So some ongoing challenges. So it is challenging to come up with efficient and effective algorithms, because keep in mind, within an in-situ environment, you're running alongside a simulation. And the last thing that you want to do is to have a very computationally expensive algorithm that slows down the simulation. Yeah, so domain researchers don't like when you introduce new features into their code, especially ones that they weren't maybe keen of initially, and having them completely slow down or even crash the simulation. That's the last thing you want to do. So it's very important for us to come up with very efficient and effective algorithms that are fairly that are high performance and very low cost compute-wise to run alongside these simulations, to try to minimize the effect that it has on the total runtime of the simulation. And sort of as a byproduct is, yeah, we want to perform meaningful data reduction, either numerical data compression or the actual reduction of, you have this abstract simulation and you want to produce images of it and try to make those images understandable to the domain researcher and having them make sense. And then finally, something I probably should have spent a bit more time on, but it's something that's constantly being researched, is machine learning for data science. So the next big push for data analysis and data science is machine learning. So I got to hand it to the computer vision community. So they've been all over machine learning for the last maybe five to 8 years, and they've sort of they've shown how useful it's been. But relative to large scale simulations, the image processing problem is a lot easier in terms of ingestion, and the data problem size is a lot easier compared to simulation. So if you have this massive petascale size simulation for many time steps, how do you run a machine learning algorithm on that? First, it's sort of the logistics. You have massive data. How do you ingest all of this data in a meaningful way? So we're constantly looking into different, even data reduction methods. So we could do data reduction on this large data and do machine learning on this data reduced problem set and see if that produces meaningful results, to try to maybe estimate the time steps in between the simulations that we don't write out to disk. And then second, there needs to be a lot more work done on this black box nature of machine learning. So end of the day, if we want to sort of reproduce these time steps in between the simulations, we have to come to some understanding of what deep learning machine learning is doing. So currently we have a very deep understanding of the physics models and what drives the simulation. But treating machine learning as a black box is a bit dangerous, because in general sense, it's kind of difficult to work with something you're not super familiar with. And there's ways that we're looking into to try to alleviate this. Is like, for example, we're trying to visualize the neural nets that are being constructed and try to come up with different ways to visualize neural nets. But definitely machine learning is sort of, in terms of machine learning and scientific computing and large data, we're in our early stages, and we see this being sort of the next go-to field that we're preparing for now. And 2-3 years down the line, you're going to see machine learning in sort of scientific computing. So that's one hot area that everyone should sort of peek into and maybe learn a bit about, which we're certainly doing as well. So that's more or less the conclusion of my talk. So I want to do a bit of an advertisement. If you like some of the cosmology simulation stuff that I showed, we have a workshop application spotlight at IEEE Viz 2020. It happened, so we don't know the exact date, but it's between October 22nd to the 30th. And I'm one of the organizers for this spotlight titled Opportunities and Challenges in Cosmology Visualization. And a bit of a preview. We go over the challenges of first we explain what is cosmology. And we have some of the domain researchers that work on these codes give sort of their take on what cosmology is. Challenges in scientific ray tracing within these massive data sets. Challenges in visualization. I already gave a preview earlier in this talk. And then different tools. So this is another tool called OpenSpace used for visualizing this type of data. So here's a link that you could go to, and there's a lot more descriptive descriptions of the different sessions. But IEEE Viz 2020, same as supercomputing, its general admission is free, so anyone's free to join. It's going to be a lot of interesting stuff. So if you have a chance, go for it. And upcoming talks as well. So like I mentioned, the foresight work. So foresight analysis that matters for data reduction. So this is a paper that we recently had accepted for supercomputing 2020. And once again, its general admission is free. Anyone could join online. It's all going to be an online conference. If you're interested in sort of these data reduction techniques like compression methods, machine learning methods, and sampling methods, look forward to this talk. We're going to cover that and the capabilities of foresight and what that entails. And then also a workshop. We also had a paper accepted at ISAV, which is an in situ conference. It's a workshop at Supercomputing, also hosted at Supercomputing 2020. General admission is free once again. And this is more related to in situ methods. So we present a framework to do in situ steering. So as you perform in situ analysis, we were able to direct the simulation as it's running and give feedback. So real time as the simulation is running, you're able to influence the simulation and produce more data products, different results. If you're not too keen on automatic methods, you could specifically in real time when the simulation is running, you could say visualize this region and it'll give you that region, or visualize these different halos within this cosmology simulation. And that's all made possible by this framework that we developed. So I apologize if I spoke too fast, if I rambled on a bit, but thank you very much. Any questions?
Thank you, Jesus. It's very interesting to see the applications that you are working with and the techniques that you have been developing. We have some questions. To start with, I've seen that you showed some examples in cosmology, and basically they come from like large scale simulations, right? So they
Right.
cover like billions of years and portions of the universe. And you mentioned at some point that one next step would be comparing these the findings of these simulations with real data, right? So
Right.
do you also work at the lab with these comparisons of what you find in the simulations and how to match it back to the possible things that you have in the real data?
Not directly. So we work more on the simulation side of things. So there's another team that handles that, and they're part of the whole LSST project in that end of the calibration. So I've actually done some work on compressing LSST data, and that was actually part of my PhD thesis. So I created a data compressor for sky survey data. But yeah, that's sort of a bit of outside of the scope of this of what we call the ExaSky ECP project. So this is strictly sticking with the simulations and the generations of these sky surveys. That so that part of the work is handled by it's like a different type of funding and a different team. So we don't do any direct collaboration with them currently.
Right, right. And you mentioned this tool called Paraview. Is it like a free open source tool that you can download and use? How is it?
Yes, it's free open source, free and open source. So I'm sure if you Google it, there's like a GitLab, and it's a large open source project. But at least in terms of us and sort of the national labs here in the U.S., this is one of the most popular tools. Other similar tools that others may have heard of are maybe Visit or Ensight, or I think even Vapor. Those are other visualization tools. So this is a tool comparable to those, but you start getting into details in terms of how they compare. But essentially, right, we feel that Paraview is sort of the most feature rich, feature rich tool. So that's the tool that we focus on most of our development on.
Very good. I have some related questions here. Professor Paula is asking, you've shown some of these applications in terms of cosmology, turbulence, but these tools that you showed, do you know if they work for other kinds of data visualization, like virtual reality visualization, or for instance, if you have data in terms of smart city sensors, could you visualize different things like this?
Yeah, absolutely. So actually, Paraview has a lot of features. One of them is actually VR support. So you could set up a visualization pipeline in Paraview, and it uses an OpenVR plugin, and you could use I actually have a setup here, and I'm doing development on that. But that's sort of outside the scope of this talk. I wanted to show it. It was pretty cool. But you could do interactive visualization inside of Paraview with like an HTC Vive, and sort of play around with the data and do sort of zoom in and out, do cross sections. So Paraview has that capability, and it uses OpenVR, and I believe it's shipped with the executable. The executable is available for Windows, Linux, and Mac, but I think only the VR stuff is enabled on Windows. Okay. So that's sort of the downside. And in terms of data, like I said, Paraview has over 100 readers for many types of different data sets. Mm-hmm. So most likely, if you're working with a certain type of simulation and it outputs some sort of format, even if it's a standardized format like HDF5, most likely ParaView has a reader for that, and you're able to read that into ParaView and mess with its different filters.
All right, very good. I have Aurea asking here, the visualizations of temporal evolution from cosmology simulations are really interesting. We could use these strategies in other contexts. These simulations may include uncertainties. So any idea of how to deal with the uncertainties in the reduction process?
So we do have another, actually didn't cover, there's actually people in our team that do uncertainty visualization, and there's a whole science behind computing the uncertainty. And certainly Foresight, the tool that we use for comparative data reduction, so numerical data reduction, we compute this uncertainty value, and we use a combination of say relative error, absolute error. Um, the visualizations that I showed don't have any error because the temporal visualization that I showed was a different. It wasn't data reduction. It was essentially doing cross validation between different simulation codes. But even doing cross validation between different simulation codes, one code being sort of the lead code, and you're trying to get one code up to speed to the other code, there's a certain uncertainty being computed there. So we tried doing actually screen space comparative visualization to see if we could say take slice A of sim 1 versus slice B of sim 2. But at the current state, that was so volatile that the results weren't really that great, because they're still constantly, even until today. So this work is maybe a few months old. Even till today, they're still doing a lot of heating and cooling refinements of their subgrid models. So that's something that we have, and we have the capability of doing. So doing even like screen space or even voxel space differencing and showing the uncertainty of that. But I did have a chance to show here. So that's something we're definitely considering too.
All right.
And that's part of the pipeline. I just didn't have any nice looking pictures to show. So they look fairly messy.
I have a curiosity. After you showed this, like you were dealing with like really big data sets, like probably some of them in the terabytes situation, right? So how does it work? You receive the parameters for a simulation and you run the simulation as you go. You try to select some sectors and visualize, or you run the entire simulation, you save, everything is sitting on the disk, and then you need to sample, which means that you need to have some policies to know where you go to the disk and load it and visualize.
Right. So currently it's a combination of both. So there's online and offline analysis. So online is the first one that you mentioned, is while the simulation is running, you do analysis next to the sim. And then there's offline analysis where you've already run the simulation and you have this massive data set sitting somewhere on disk. And it becomes sort of an IO problem of having, one, you need the resources equivalent to what simulated the data to even read in the data. So that's where sampling comes in. Maybe you want to subsample the data smartly without having to read in a petabyte of data to just visualize it. So there's different strategies that we use there. The one that I focused on here was sort of the in situ case of you want to do analysis as a simulation runs. So to give it a bit of a context, when they run these big simulations, they already output at regular intervals. So maybe every 500 to 1,000 time steps, they do a restart dump. So they're restart, the kids of the simulation crashes, they're able to restart it. So these restart dumps are what we use for visualization, sort of offline. And these are sort of the high resolution, massive visualizations that you see sort of in videos and movies and on websites. Alongside these simulations, we have in situ techniques that run at times more frequently than the restart dumps. So say restart dumps are every 500 time steps. These in situ techniques may run every 10 time steps. So at a much finer scale. And at this much finer scale, we might not get as amazing visualizations as sort of the big scale ones, but we could get sort of samples and previews of how the simulation is progressing at more frequent intervals without having to write to disk, other than the images themselves. So the data is already in memory in situ. you have access to the data in memory, so we could do a very quick visualization, write the images to disk, and then proceed forward with the simulation. So that's what I meant by trying to come up with a meaningful way of coming up with these metrics. So doing this feature extraction, identifying the regions that you want to visualize, and sort of pre-bake those into this this in situ routine to run at regular intervals versus the much more broader restart dumps to disk.
Right. About that example that you showed in which you wanted to detect the halos. So as I understood, you had like a big simulation, right? A very complex one. Can you go back to that slide, please? This one. So it seems that to be like a very complex and large file that you might have sitting in the disk, and then you need to go with like small pieces of it each time, right? So are you developing the classifier on top of this, or it's a series of statistical operators that you apply on the window and you try to detect based on, for instance, some disturbance analysis, a texture or something? So do you have here the step of like machine learning algorithm trying to learn these differences, or you have other techniques?
There's statistical techniques. So the brute force method is sort of a friends of friends computation. So you do a particle. So each particle, you compute the distances between each particle versus every other particle within the region. And there's ways to speed that up in parallel, but it's still relatively slow. So it's sort of a brute force approach of computing distances, and you compute this notion of friends of friends. So this particle is distant this much from these other particles, and that forms a cluster, and that cluster forms a feature of interest. And during the large runs, this is done in situ. So actually, I kind of cheated a bit, and I said, ideally, we want to have high-performing in situ algorithms. It turns out that the Halo Finder is very expensive. In fact, the Halo Finder takes more time to run than a single time step in the simulation. But because it's critical to their analysis, they just have to do it. And they have to rely on programming models to try and speed up this Halo Finder. And they're constantly, even today, that's still, they're reconsidering rewriting the Halo Finder just because it takes so much time during compute time or during this in situ evaluation time. So yeah, so these things are generally run in situ next to the sim, and instead of writing out the entire state of the simulation to disk, which is already done in the restart file, they write out Halo files. So these are smaller, sort of bite-sized binary files that just sort of cut out the Halo region and write out those particles to disk. So you end up writing many small files to disk, and that introduces a lot of challenges in terms of file I/O. If anyone's written millions of small files to disk, you know how that kind of kills file systems, and that's a big no-no. So there's sort of there's file systems guys on this project too, try to optimize that. But in terms of offline approaches, typically Halo Finders aren't run offline. They're run with the sim in situ. If you have a small enough data set, you could run them offline. Like we used in our case for Foresight to do this Halo versus Halo, lossy versus original analysis, just because the data is more manageable. It's a few gigabytes versus petabytes of data. But you brought up machine learning also, and that's actually one of that it's not really a milestone in the upcoming years, but that's definitely one of the regions of interest that's in the early stages that the domain researchers are interested in looking at, to see if you can use some form of machine learning to predict the different regions. But this goes back to the problem of how do you even process a petabyte of data and run it through your machine learning algorithm. And yeah, that's constantly a problem that's being worked on. So one solution from one of our colleagues, specific to turbulence data, what he found is, so this goes to some of the results in the supercomputing paper about looking into machine learning autoencoders for data compression. What they found was, instead of ingesting the original 1024 cubed turbulence data and use that to do the training. They run wavelet analysis techniques to do data reduction. So they use wavelets for data reduction, and they train on the wavelet coefficients. So they're doing data reduction, and that actually produces some pretty impressive results. So
Yeah.
that's one way of tackling, say, the whole.
This was my next question. If you could do some kind of a hierarchical analysis, and based on that, try to predict candidate regions to have the halos. Yeah. Out of curiosity, there is a question here from Paulo. How much time does a simulation like this one take to run?
So this specific one, I think it was ran in 2018 on Titan, which is the biggest cluster at the time at Argonne National Lab, which is where the hack team resides. So this run is, for example, one of the hero runs. So a hero run is something that takes up the entire supercomputer, and they request allocation ahead of time, months ahead of time, and they have like a week of the entire supercomputer.
A week
alone.
Or a week worth of the top computer system that you had.
Yes, a week worth. So they halt all allocations and they give you, I want to say a week, probably less, a few days, because I can't recall this. I wasn't there for this run. I was still a student, so I don't know the exact specifics for this run. Mm-hmm. But these types of codes, they call them, I think someone joked, like supercomputer killers, because mm-hmm. these are so intensive, nodes end up failing. Regardless, either it's maybe a hard drive dies, some of the fans die on some of the nodes, but these simulations stress the entire system so much that they're supercomputer killers, and these are benchmarks for supercomputers. So when Titan comes out in 2021, 2022, this is going to be one of the benchmark simulations to stress test and benchmark the entire 1.5 exaflop supercomputer. So that's the sort of scale that we're working with. So these are sort of like the top massive simulations.
It's very nice to have you talking to us here today, because everybody talks about we are dealing with machine learning and we are doing big data, and they say that we are training classifiers with like millions of examples. Those cases are like tiny ants compared to the simulation data that you were talking about.
Yeah,
here.
So like this run is hundreds of trillions of particles for one time step. One time step. So this is a massive problem, and this doesn't even count on what's going to be ran in about 2 years.
And of course, when you think about how you go for the next step, I mean, now you have this data, and then you think about, okay, now we need to apply machine learning. So everybody says the whole time that machine learning is all about big data, but they don't know actually what they're talking about, because when you have really big data, then you have a whole new world of adventures and challenges, right? How to read the disk and how to process like tiny portions of the data each time. So the challenges that you mentioned here today are very, very interesting to like open the mind for, okay, this is really big data, and what we are doing, what we need to do when we go to that kind of data. So I agree with you that the next barrier will be how to match this whole amount of data with machine learning, right?
Right.
And of course, you need to think of the algorithms. You need to apply efficient algorithms that can process fractions of the data, save everything, because you can have a crash and other things.
Right. And there's still research to be done on how, say, doing machine learning on small scale data, and how that, if that even scales with larger data. Because of course, larger data, you have more complex physics and interactions. And it would be interesting to see whether, if you do training on smaller scale data, say tens of millions of particles scaling up to 100 million, a billion, 100 billion, a trillion, to see if the models at the lower levels scale up to the higher levels. It would be miraculous if this works. But then again, like I said, it's essentially a black box, and we got to be careful, and we got to try and understand as best as we can what's going on.
Exactly.
So, yeah.
Exactly. This is what I try to say to everybody in my team and in the classes that I teach. you cannot use, you cannot develop algorithms that are like black boxes. You need to open the Pandora box and understand what's going on, right? I have
Right.
one other curiosity here. So when you receive a new data set, so suppose that someone, some experts ship a new data set to you, and you need to do some initial analysis of that data. So what's the typical first steps that you take to try to gain some understanding, initial understanding of that data? Because we are talking about
Yeah.
big files, so you cannot just do at random.
Right. So we have smart sampling methods. So we have techniques like stratified random sampling. We have entropy-based sampling. At least specific to particle data sets, we try to do some form of sampling because I should have included some images. If you try to visualize this giant block of particles, it's just a block of data. You can't see inside of the data because it's all just particles. It's just a giant cube of particles. So it's sort of a requirement that we need to do some form of sampling. And we have, in terms of the structure itself, we use octrees to try to do, we combine octrees and stratified random sampling to do a non-biased form of sampling initially to try and do maybe 1% of the data and visualize that and show sort of the different regions. So 1% of the data seems to be a pretty good initial approach when we get a new data set. And then if you ramp it up to say 20%, there's already so many particles and it's so dense that you obstruct whatever you're trying to see inside. So stratified random sampling and entropy-based sampling are two of the more prominent methods that we use to look at these massive particle data sets. And I didn't include it in this talk, but the entropy-based stuff is actually a paper where I was a co-author 2 years ago, where we got a workshop paper where we introduced this entropy-based subsampling.
Can you send me later these references for the smart sampling techniques that you're mentioning, some of them? Then I can share it with everybody in the talk. Those are very interesting approaches because we need to have like an initial feeling of the kind of data that we are talking about. And
Exactly.
It's complex to process the full data right at the beginning, right?
Right. Yeah, I'll forward you that paper. I actually didn't add it here. It actually skipped, but it was a 2019, 2018 paper by Ion Biswas was the main lead author on that. I was like the third author on that work. But it essentially it works within the realms of cosmology data, and they do this smart sampling to try to extract regions of interest and to do a very initial visualization. And they actually do we do some error analysis on that. Yeah, so
And,
I could definitely forward that.
As of today, would you say that cosmology data is like the most computing intensive data that you receive, or you have others?
Yes, but by a long shot.
A long shot?
Yeah, because I mean, this is sort of the exascale computing project. So by definition, we're targeting these next generation exascale computers. So we're on purpose refining our models to run at this exascale level to produce these massive data sets, because we have these nice new toys coming in about a year or two with new hardware, new software, and we're trying to push them to the limits, like new GPUs, new CPUs.
I would love to have one fraction of that.
Yeah. Well, I'm not sure if they have open proposals. I think the first year might not be open to open proposals, but actually, unfortunately, I don't think they're open.
And these computers, they sit at Los Alamos lab or at, in other places?
They sit across the different labs. So usually it's sort of a round robin on what lab gets the next coolest toy. So it turns out that in this case, Oak Ridge is going to get the next one.
All right.
And then Argonne is going to get the next one. And then, so like Los Alamos had sort of the best one about 3 years ago. But now it's a bit outdated and people still use it, but it's not as fast as like what's currently at Oak Ridge. But it's sort of a bit of a round robin in terms of which national lab gets the next the next best toy to play with. But yeah.
All right. So Jesus, thank you very much. I don't have any last question here. So I would like to thank you once again for accepting the invitation for this nice talk.
Thank you for the invite.
Thank you. It's always interesting to see like applications and problems in different areas, and we learn a lot when we have this kind of knowledge sharing. So thank you very much, and everybody, thank you for being here today. I talked to Jesus at the beginning, and he's gonna ask for authorization for making available the video of this presentation. And once we get that, I will make it available for everyone, okay? Thank you very much, Jesus. Once again, thank you. Good evening to everyone. Bye-bye.
Okay, thank you.
Thank you.
Bye.